Hi, Sean.
Hello, Professor.
How was your Thanksgiving?
It was all right. It was good. How was yours?
It was nice, thank you. I
Hmm.
enjoyed going to my sister's house. They have a fireplace, and it was really nice to see everybody and sit around the fire.
Oh, that sounds nice.
It was lovely. So, what can I do for you today?
Um, I
What would
would
you
just like to. So 7.1 and on, it's like the test is finally is cumulative, right?
Right, it is. And so 7 and 8 will be on the final exam.
Okay. So I would just like to just start off with 7.1.
Okay, so in section 7.1, did you watch the video?
I have not yet got to the videos. I wanted to like get it from you first, and then I like
Well,
because
the
I feel like
video
it's better if
is
I ask
me.
questions.
The video
Yeah, I
is.
mean, yeah, it's you, but like if I get my questions out right, like now, I guess like it's kind of like a lecture type thing where I can like ask questions while you're doing it.
Okay.
If that makes sense.
It does, but it's not a good use of our time because if you'd
Okay.
watched the video, then we could be talking about material that you didn't understand or material that I haven't given you a video on. But let's just look at the definition of a function. Okay, so
Mm-hmm.
we're given non-empty sets, A and B. So we start with those. We're going to let F be a subset of A cross B. We say F is a function. There are lots of subsets of A cross B, okay? But we say F is a function from A to B if two things happen. One, for each element, say little x in A, there is at least one y in B such that x, y is an element of F. And the way we might write that would be that, f of x equals y. Okay, and a function from A to B, that notation is f goes from A to B. I'm not looking at my notes. I'm just trying to remember them. And two, there's one other thing. For each x in A, there is at most one y in B. So actually, we could say this in one sentence, but I'm trying to make a point such that xy is in F. So for every x in the set A, which is going to be called the
Mm-hmm.
domain, there is at least one y in B and at most one y in B, such that the ordered pair x comma y is in F. All right. So A is the domain of F. B is the codomain of F. Maybe you used to call that the range when you were in high school, but it's really the codomain. Is this in focus?
Yeah.
Doesn't seem to be in very good focus. Okay. And then the big deal is you've got to have one range element or codomain element, it's really a range element associated with each x in the domain A. So here's an example. Let's just look at a little finite example. Let's let A be the set containing little a, little b, little c, and little d. And let's let B be the set containing 1, 2, 3, 4, and 5. And we're going to define F, which is going to be a subset of A cross B, as this. F is going to be the set of ordered pairs where A maps to 1, B pairs with 2, C pairs with 4, and D pairs with 4. And the question is this subset of A cross B? It's clearly a subset of A cross B, right? Because it's ordered pairs with first coordinates from A and second coordinates from B. Is F a function from A to B? All right. So really we're asking, is there for each X in A, there exists, this is new notation, a unique Y in B such that X comma Y is an element of F. That's kind of a shorthand formal definition. It means for every X in the domain, there has to be a unique, exists with an exclamation point, means there exists a unique Y that pairs up with any given, a given X. So do you think that this is a function
Um,
from A to B?
no,
Why not?
because there's two fours and like the C and D order pairs.
Okay, and that's exactly why we're looking at this particular example, because that is a common misconception. It doesn't say that each Y in B has to have exactly one X in A that maps to it. It says for every X in A, there exists exactly one or unique Y in B that it pairs with that X. So A only pairs with one element of B, B only pairs with one element of set B, little c only pairs with one element of set B, and D only pairs with one element of set B. So in fact, this is a function. Each X in A is paired with exactly one Y coming from B. In other words, we do not see, oh, suddenly it looks much better. But it's like my internet just kicked in or something. There is no other ordered pair besides A comma 1 that has A as the first coordinate. That's the only requirement. So you could think about it this way. No element X from A appears as a first coordinate more than once. But each X in A does appear as a first coordinate. So each X in A appears exactly once as a first coordinate. It's okay if an element of the codomain B appears more than once.
Okay.
And if we draw a picture with an arrow diagram, here's A. It's got little a, little b, little c, and little d in it. And here's set B. It's got 1, 2, 3, 4, and 5 in it. An arrow diagram is a really nice visual, and we're just looking to make sure that there's an arrow coming out of every element from the domain. The domain is A. So A goes to 1, so we would draw an arrow from A to 1. B maps to 2, so we draw an arrow from B to 2. C maps to 4, and D maps to 4. Make sure you put the heads on your arrows. It's okay that two arrows hit the same element over here in the codomain. We just don't want two arrows to come out of the same domain element. So if we want to look at a couple of non-examples of functions so that we can really see sort of a whole picture, here's a non-example. We'll use the same A. I think it's with the A, B, C, D, little a, little b, little c, little d. And B has 1, 2, 3, 4, and 5. We'll call this non-examples. We're going to let F be a subset of A cross B, and F is going to be the order pair where little a maps to 1, little a maps to 2, little b maps to 3, little c maps to 4, and d maps to 5. And that's not going to be a function because A is being sent to two different image points, okay? So it's not a function. If you drew a picture, here would be little a, here would be set A, and here would be B, 1 and 2 over here. You'd have two arrows coming out of A, and that breaks the definition of a function, okay? This is, no good. The other way that no good. The other way things can go bad is if let's build a G that's a subset of A cross B. Remember, a subset of A cross B could be any ordered pair any set of ordered pairs, right? With the first coordinate from A and the second coordinate from B. So what if G looks like this? What if we send A to 1, B to 2, and D to 3? Is that a function?
Yeah.
Well, did every element of the domain A
No.
appear as a first coordinate? Right, so it's
No.
not a function. And it's
Oh, so each of them had to be used. Okay.
that's exactly right. If we go back to our definition, for each x and a, there's at least one y and b, such that x, y is an f, and for each x and a, there's at most one y and b. So for each x and a, there's exactly one. There exists
Okay.
exactly one y. Uh-huh. So, if you drew the picture here, the problem would be that C wouldn't have an arrow coming out of it at all, right? I mean, there's nothing else that could possibly go bad in case you were confused about the fact that codomain elements could have several arrows pointing to them. There's no problem with that. You just can't leave anything behind and you can't send anything to more than one image. Okay?
Mm-hmm.
All right, so let's ask some of the other, so that's the definition of a function and a couple of sort of starter examples. We've got Stephen in the room and Fakir's in the room. So I don't know which of you appeared first because I was sort of busy writing. Do either one of you? Stephen was first. Stephen, do you have a particular question? And we don't have to just talk about functions because there's a whole video on 7.1 and 7.2 that's been posted.
Well, as of right now, I don't have any questions, but along the line, if I have any questions, I'll ask.
All right, Fakira, how about you?
I was wondering if we could go over the extra credit on the last special homework.
Uh-huh. Can you tell me what it was? Can you read it to me?
Sure, give me 1 second.
And I can also look for it. Which class are you in?
Sorry, I'm in your Tuesday to Thursday, 3:30 to 4:45 p.m.
Okay, so you're in Tuesday, Thursday.
Mhm.
All right.
Okay, let me see. It is the extra credit recall. It says we say a collection of sets A1, A2 up to A3 is pairwise disjoint or mutual disjoint if none of these sets share any elements in common with any of the other sets, i.e., if
Okay, so this collection is, and is it a dot, dot, dot after the A3?
yes, ma'am, it's A comma A2 dot 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 AK.
Okay, so I'm talking about a finite collection there. All right, so we're not using the axiom of choice. Okay, so A1, A2 up to AK is pairwise disjoint if AI intersect AJ is equal to the empty set whenever I is not equal to J. All right, so what were you asked to do? You said this was extra credit on, this might have been the worksheet for the Monday, Wednesday people, but for you all, it was homework number 11, wasn't it?
Yeah, it was the extra credit for the homework.
And so what did I ask you to do with that?
You asked, they said, do review the definition of partition, create
Mm-hmm.
your own definition for an infinite index collection of sets that form a partition of R plus.
Oh,
In
okay,
other words, your collection needs to satisfy these properties.
right. And so a collection, let's just review the definition.
Yeah,
C of
sorry.
subsets of A is a partition. And there, you might start the indexing at 1, you could start it at 0. A partition of A if 1, that collection, each of those subsets is non-empty. 2, we have pairwise disjointness, right? AI intersect AJ is empty. Do you remember, do you feel comfortable with pairwise disjointness? Did you review the class notes on that?
I did review it, but I wasn't comfortable enough to where I was able to successfully complete the extra credit without confusion.
Okay. And then the union from say I equals 1 to whatever k of the A sub I would be all of A. Now that's if it's a finite collection, but if it's an infinite collection, if C is infinite, then C just looks like, I don't know, you could index it starting at 0, you can index it starting wherever you want, but let's just say we started at 1, we don't have to. If it's an infinite collection, then 1 and 2 are the same, but 3 becomes the union from I equals wherever you're starting. It might be 1, it could be 0, to infinity of the A sub I would be A, okay? It would be an infinite union. But so pairwise disjointness is a little tricky. And we should probably just make sure you understand pairwise disjointness. It just means if you take any two of them, AI and AJ, as long as they're not the same set, that's what I not equal to J means. It just means we picked an AI and an AJ that are actually different among these. We just don't want to like intersect A2 with A2 because it's not empty. So its intersection with itself would be itself, and that wouldn't be empty. But if you take like A1 and intersect it with A2, they wouldn't have any elements in common. So their intersection would be empty, for example, or A1 intersect A3. That intersection should be empty. A2 intersect A3. You get my drift? A1 intersect A4, A2 intersect A4, A3 intersect A4, all the way to A1 intersect AK, A2 intersect AK, up to AK minus 1 intersect AK. Those have to have empty intersection if you just take any two of them. So shall we look at an example of a
Yes,
pairwise
please.
disjoint collection?
Yes, please.
So if we let A1 be the set containing 1, 2, and 3, A2 be the set containing 4 and 5, and A3 be the set containing 6, 7, 8, 9, and 10, for example, okay, then are the sets A1, A2, A3 pairwise disjoint, or we could put them together in a set called curly C and ask the same question. We could just say C is the collection that has A1, A2, and A3 in it. You can say it different ways. But the point is, we're going to take these two at a time and see if they ever have anything in common. So, like A1 intersect A2, we'll have to check that out. But then we'll have to intersect A1 with A3 and see what that is. And what would be the other pair that we would need to check?
A1 with AK.
Well, we only have three sets here, so K is 3, okay? So if we say we're going to look at the intersection of these two sets, right?
2 and 3.
Yeah, 2 and 3. You see, because it's only we've got three indexing numbers. Our indexing numbers are 1, 2, and 3, and we're choosing two at a time. It's 3 choose 2, which is, three indexing numbers. We have 1, 2, and 3 as our indexing numbers. We're picking two at a time. And if you calculate that, that's 3. There are 3 different ways to pick an I and a J from I, J, K, right?
Yeah.
Where they're different.
Okay.
All right, so what does A1 intersect A2? Let's take a look. Well, A1's got 1, 2, and 3 in it, and we're going to intersect that with set A2, which has 4 and 5 in it. What is that intersection going to be? All right, so let's remember what intersection means. It's our AND operator for set land. So an element is in the intersection of these two sets if that element is in this set and in the other set. It has to be in both of these. Are there any elements in both of these sets?
No, ma'am.
That's right. So what is the intersection then? It's an empty set. There's nothing in there. Or you could write it like this, just set brackets with nothing in between.
Okay.
There is no element that's both in A1 and in A2. You get it?
Yeah.
All right, great. So that's really good. What about A1 intersect A3?
There's none.
There's none. So the intersection is the empty set. What about A2 intersect A3?
There's none as well.
So what is the intersection going to be then?
An empty set.
That's right. So the answer is yes. Because if we take any two of them, their intersection is empty. All right. So what I asked you to do is to just think about all of our discussions about interval notation and indexed intervals. And we looked at the real number line, and we know, so this is the reals, and here's 0. And if we want the positive reals, we don't include 0. We're just including all the real numbers that are strictly positive, right? So it's everything bigger than 0. There's an infinite number of real numbers, a lot more than just the integers, because it's all the real numbers that are, in between the integers too. So R plus If you go back and look at our interval notation notes from homework number 2 and also from recent homework class notes, R plus goes from 0 but doesn't include 0. That's why we have a soft bracket there to infinity. Do you remember that?
Yeah.
And we want an infinite collection. And we can index it however we want. We can start with whatever indexing number we want to start with. We can start with 1 if that's convenient, or we can start with 0 if that's convenient. We want an infinite collection, C, that partitions R plus. And we're asked to use interval notation. So I don't know if you missed the lecture, Bakira, but we looked at this idea in one of the examples in the lecture notes, in the class notes. And it turns out we could take the set that doesn't include 0, but goes up to and does include 1, right? We could call that set A sub 0. So, A sub 0, don't include 0 because we don't want 0, but go ahead and include 1. Then we could pick up right there and build A1. We're not going to include 1 because it's already in A0, but we're going to go ahead and include 2. So we get this bit of the real number line. And then we could say, oh, looks like it might work because we're filling up the real number line, but these are disjoint sets, and we'll be able to define these in a way that we can just keep on going. We can just keep this game up. We can play Christmas games. We can see what I mean? You could just keep on going and fill up the whole number line with little sets that are 1 unit long, but don't overlap with each other because you see A0 contains 1, but A1 would be the only possible set that could possibly overlap with A0, and they're not going to be able to overlap because A1 doesn't include the 1, see? And same with A1 and A2. A2, there's no way A2 can overlap and have any elements in common with A0 because there's a big space between them, right?
Yeah.
So the worst case scenario would be if A1 and A2, because they seem to meet right there, could possibly share an element. But we fixed that by putting the square bracket on one side and the soft bracket on the other side so that they can't possibly touch. So our collection could be A0, A1, A2, just keep on going forever because we want to fill up the whole positive number line, right? Where A sub K is, oops, I want the soft bracket here because of the 0. I don't want to include the 0. Go from K to K plus 1. See how that works for different integer values of K?
Yeah.
For all integers, K greater than or equal to 0. So that works. That's a good question. All right, other questions?
Thank you.
You're very welcome. I'm glad you asked. That's kind of a fun problem. More like a puzzle than a real math problem is, but we do have to understand things, right? We have to understand intersection. We have to understand that pairwise disjoint means they just can't share any elements. So somehow, that they can't be touching each other, but they can get real infinitely close to each other. A1 does not have a smallest element. You can get as close to the number 1 as you want in this set, but we can never attain 1. But there is no smallest element in this set A1. The minute you think you have a smallest element there. So here's 1. Okay. And let's just make it really big. Okay, so here's 2. So here's all the elements in A1. The minute you think that you have found the smallest element in A1, let's just say you've picked this element X. I can get my microscope out and I can zoom in here, my microscope, and I can see that there's lots of space. Microscope. Microscope, I like it. There's a lot of space, actually, between X and 1. So the minute you think you found the smallest element in A1, I'll sneak in here and I'll pick one that's even closer to 1, like X over, 1 minus X over 2 or something. I'll call this X2 and we'll call this one X1. There's ways to construct it. I guess it'd be 1 plus X. See, what would be 1 plus X over 1? Oh, X1 over 2. Yeah. X2 could be 1 plus X1 over 2. So it's halfway between 1 and X1. So it's smaller than X1, but it's still in there. Anyway, that's the idea of having those soft brackets. They bound the set, but there's no minimum element if that soft bracket's on the left. Other questions? Sean, did you have another question? Did you want to continue?
Yes, this is about like an older question though.
That's fine. Anything.
Can we go over? I'm reading a question from his test two. Consider the integer n equals 7,056, and then the egg then it says find the standard form for n, and
Standard
then
factored form?
yeah,
All right, so standard factored form. Let's just go, and then anything else you wanted to do with that?
is n a perfect square? Explain for credit. I didn't know how to.
Okay. All right, so let's look at this example that you pulled up. N is 7,056.
Yes.
All right, so we're gonna A, find the standard factored form of N, and then B, is N a perfect square? Now, do you remember what a perfect square is?
Not off the top of my head. I don't know the formal
Let's review
definition.
the definition. An integer n greater than or equal to 0 is a perfect square. And in the notes, I might have these variables the other way around, but it doesn't matter if n equals x squared for some integer x. So 0 is 0 squared, so it's the first perfect square. What's the next perfect square?
2. Where's it 1?
Two's not a perfect square because the square root of
Oh,
two
four,
is
four. My
in,
fault.
so one, okay. What
And then
now? Yeah, if you want to look at what 2 squared
yeah,
is, what's that next perfect square?
4.
All right, and then you're looking for the next one would just square 3, right?
Yeah.
All right. So that looks familiar, right? So let's go ahead and write the solution to this. And I don't think we really need a calculator because the first thing we're going to do is we're just going to start pulling out copies of 2. This is even, right? Because 6 is even. We know we can write this as 2 times, okay, so let's divide this thing by 2. Half of 7 is, or half of 70 is 35, and half of 50 is 25. So we've got 3,500, and then half of 50 is 25, and half of 6 is 3. So if we add those together, this should be right. Now this is, so we can't break the 2 down, obviously, but we can break down 3528 because it's not prime. And in fact, it's even, isn't it?
Mm-hmm.
Pull a 2 out of that. So 2 times 2 times, okay. So half of 3,400 is 1,700. Then we've got 128 left, and half of that is 64. So it's 1,764. You can check me. Well, so we pulled out two factors of 2. Now let's see about the 1764. It's not prime, so let's break it down. Oh, well, we can sure factor another 2 out because 64 is even, 4 is even, right?
Mhm.
So half of 1600 is 800, and then we've got 164 left. And what is that, 82? So it's going to be 882. Oh gosh, we can even still pull out another copy of 2. We just keep doing this until we can't pull out any more copies of 2. And what is that going to be, 441? I think we're finally done with the 2s.
Right.
But 441, I don't know if it's prime or not. I'm just not that smart. I know it doesn't have a 2 in it, but it might have a factor of 3. And we have a really nice little algorithm for checking if 3 divides a large number. Just add the digits of the large number up. And if 3 divides that sum, then 3 will divide that large number. So let's add the digits of 441 up. It's 4 plus 4 plus 1. What is that?
9.
And 3 divides 9, doesn't it?
Yes.
So 3 will divide 441. So we know we're going to have a copy of 3 here. Now, how many times does 3 go into 441? Well, 3 goes into 300 100 times. And then we've got 141 left. Well, 3 goes into 120 70 times. And then we've got 21 left, so 7. So it's 177. You can check me. Of course, you were allowed to have a calculator on the test. All right. Now, we'll never see any more 2s because if we were going to see another 2, it would have been in 441. But we might still see another 3. So let's add the digits up and see if there's another copy of 3 that we can pull out of 177. Can we? What's 1 plus 7 plus 7?
15.
Uh-huh. So is 3 going to divide 177?
Yes.
Uh-huh, because it divides 15. I'm going to start conglomerating this. This is 2 to the 4th, okay? We know we're going to do that eventually. We might as well start doing it now. And then we've got a 3, and now we have another 3. And when we pull 3 out of this, let's see, 3 out of 150 is 50, and then 3 out of 27 is 9. So I'm getting 59. Is that right?
Mhm.
Yes. All right. Now, does 3 divide 59?
No.
Because it divides 60. There's no way it can divide 59. All right. Now let's look at 4. Nope, 4 is not a prime. What's the next prime? 5. Does 5 divide 59?
No.
Nope. Does 7 divide 59? Because that's the next prime after 5.
Yes.
7 divides 59?
Yeah, because it's 5 plus 9 is 14.
That trick where that only
Oh,
works
that's only works for 3? That only
that
works for
only
3?
works for 3 and 9.
Oh, okay, okay, okay,
It
okay.
only works for 3 and 9. I'm so glad we had this conversation.
Okay, all right.
Yeah, because 7 times 7 is 49. 7 times
Yeah.
8 is 56. 7 times 9 is 63. We're jumping over 59. All right, and what about 13? 11 doesn't go in here, right? Because that'd be like 44, 55,
Yeah.
66. What about 13? Does 13 divide 59? In fact, it's
Um,
59 prime.
I don't think 59 is
Did I make a
prime.
mistake? Can you multiply these together with a calculator and see if I did that right?
Yeah, I can.
Do that because I'm wondering if I've made a little mistake here. 17 is 17. 13. 13 times, no, it's not 13.
Nice stop. No, it
Is,
doesn't. Let's stop.
is it right or is it wrong?
It's not 13.
No, no, no. I'm just saying, can you multiply 16 times 9 times 59, please? Do you have a
Yeah,
calculator handy? Because I don't have a calculator with me.
I get something like higher than 7
So,
times
so
15.
there's a mistake here. All right, so we need to back up and find the mistake. Because if I multiply 16 times 9,
I think it's at the 177, the 441.
Uh-huh. What should it be?
So
Should it be,
441 divided by 3 is 147 instead of 177.
I knew there was something wrong. Thank you so much. That's right, because 150 times 3 is 450. That's too big. This is 9 less. And that would be, that's right, that makes sense. Because 3 times 3 is the 9 that we're missing. Thank you so much. I knew there was something wrong. Okay. All right, so does 3 divide into 147?
Yes.
All right, let's do it right then. All right, so 3 goes into 120, 40 times. And we got 27 left. So what is that, 49?
Yes.
Sure, because 3 times 50 is 150, right? And 147 is a jump down. If you jump by jumps of size 3, right? Right, the difference is 3. It's 49 times 3. Great. Now what is 49? Is it prime?
Yes.
No, you should know this one because it's a perfect square.
Oh,
If you keep going, what is 7 squared?
49.
All right. 5 doesn't divide in there, and 3 doesn't divide because 3 doesn't divide 4 plus 9, which is 13, but this is 7 squared. All right, so we're done because we can't break these down any further. We got 4 copies of 2, 2 copies of 3, and 2 copies of 7. Now, we had a long discussion in class about a couple of facts about perfect squares and perfect cubes. And if you go back and look, we discussed and we proved that the standard factored form of a perfect square has all even exponents. Because if all the exponents are even, like 4 is even, 2 is even, and 2 is even, then we can break this up and pull that 2 out and have 2 squared times 3 times 7 quantity squared. That's our x squared. X is the square root of this, which is 2 squared. See what I mean? So it is a perfect square. And there were a couple of ways that you could, get to that. You could just put it in your calculator, take the square root, and you would see that it was an integer. But this is really what I was looking for, was for you to remember that this fact that we proved, not only did we see it in class, we actually proved this in class, that we could always show a perfect square has to have all these exponents, not the bases, because a lot of primes aren't even, like 5 and 7 and 11, and most of them aren't even, right? It's only 2 is the even one, but all these exponents, if they're even, then you can pull a 2 out of them and just use laws of exponents, right? And that's your x. That shows it's a perfect square because n is equal to 2 squared times 3 times 7 quantity squared.
Okay. Thank you.
You're welcome. Guess I need to dig out go ahead and get my answer keys dug out of my envelope and scan those and get them posted for y'all to study. I need to make a folder called tests, right? And have all the tests with the solutions. I need to do that this week, don't I?
Yeah,
Yes,
Well,
that was nice.
will do. Absolutely, we'll do that. Other question? Still got 15 minutes. We can go a little longer if we need to.
Um, try to question. Oh, I know I have more questions. Um,
Anybody?
Can we go over proofs by mathematical induction?
Uh-huh. Is there a particular problem that you would like to see?
Uh, let me find. I think I have one.
Hard for me to pull those just out of thin air. But if there's a particular problem,
I don't think I have a particular problem. I just the concept of it. Not not like the concept, but like the breakdown.
of just the general stuff.
Yeah.
Okay. All right, so when we're trying to prove a statement, that's some kind of statement about an integer n, when we're trying to prove that it's true no matter how large n becomes, then we're going to use proof by mathematical induction. Okay? And the idea is this, the principle of mathematical induction is a great big if-then statement. And we're not ever going to prove it. We use it. We use it by satisfying the hypothesis of the principle. And the hypothesis is a two-part hypothesis. And what we do is we prove the hypothesis of the PMI holds. And then we invoke the PMI and get the result for free. All right, so the PMI says, let P of n be a predicate statement concerning an integer n. It can be one of many statements, and we can look in the book and get some examples. We need to work through a few. If P of n naught is true for some integer n naught, that's our bottom step, and P of k implies P of k plus 1 whenever k is some integer with k greater than or equal to n naught. If we can prove that these two things hold, then what we get for free is that P of n is true for all integers n greater than or equal to whatever that bottom level was. Okay, so intuitively it's like this. We prove that we can stand on the bottom step of a staircase, okay? So it's called the basis step. We just prove we can get on this staircase. So we prove that we can stand here, okay? Then we just say, okay, we know we can get on this great staircase. Now let's just assume that we're on step K. So this is called the inductive hypothesis. We assume that we can stand on step K. What we wish to do is then show that we can step up our wish is to step up and show that we'll be able to stand on the K plus first step. If we can do that, then we've proven we can get on the staircase, and then we've proven that no matter what step we're on, call it K, we can always step up. And that means we can just keep on stepping up forever and ever, and it's true forever after. N goes to infinity. Okay?
Mhm.
So that's the intuition behind the principle. The work that we have to do is to prove that we can get on the bottom step, and then we wish P of K plus 1, we assume P of K. And that process is called the inductive step, where we prove that if we're on a step, we can always step up. So our work is to prove the basis step and prove the inductive step. And there's always just a real kind of set way to do it, especially for the kinds of formulas that we like to prove. I think there was one really nice formula. What was it? The product from I equals 1 to N of, what was it? 1 minus 1 over I. I think it turns out that that equals 1 over N. Isn't that right? Let's see if that's true. Let's see if we can prove that. In fact, let's just make sure we even understand what this says, because a lot of times when we're writing product notation, I think students might get a little bit lost about what that really means. Okay, so we're going to prove it for n greater than or equal to 1, because that would be the smallest n that would make sense, because the lower limit of the product is 1. We can't have the upper limit be smaller than the lower limit. So let's just take a look. When I is 1, okay, P of 1 actually says this. It says, we just are going to take the very first factor, just when I is 1 and stops at 1. So we're going to say 1 minus 1 over 1. This isn't right. It's not right. It's not that, right? Because 1 minus 1 over 1 is, I wonder if it starts at 2. Maybe it doesn't, maybe it's not true at 1, but maybe it's true at 2. Because sometimes these are not true at 1, but they're true later. Let's try I equals 2. Is it true for I equals 2? Is 1 minus 1/2 equal to 1 over 2? Yep, it is. But look, I want you to understand, this is P of 2. When I is 3, and we're looking at P of 3, this product isn't just a single factor. We start with 2 and then we go to 3. So it's 1 minus 1 over 2, because that's what this expression is when I is 2. Oh, did I say I equals 2? I guess I should have said N equals 2. Yeah, sorry. N equals 2. N equals 3. So we start with I being 2, and we have this factor times, because it's a product, but then we're going to go up to 3. So the next factor is 1 minus 1/3. Okay? Let's see if this is actually equal to 1/3. I'm not sure that this is a true statement. I might have to go check the book. Let's just check it. If it's not true for 3, then it's not the right statement. All right, so this is 1/2. This is 2/3. Oh, that is 1/3, right? Because the 2's cancel. I think this is the right statement. I think it starts being true at 2. It wasn't true for 1, but it's true at 2. Do you see how when n is larger, what's happening on the left-hand side is this product has more and more factors. See, when n is 4, first it's 2, and we have 1 minus 1/2, but then we increment and it's 3, and we have 1 minus 1/3 for the next factor. But then we go all the way up to 4, so we have 1 minus a fourth, and that will be 1/4 because it's a telescoping product and stuff cancels. This will be 1/2 times 2/3 times 3/4. And this 3 will cancel with the 3 in the 3/4, leaving 1/4. So it is true. So this is one that we can prove. And that's actually one of the ways that you might try to just sort of check and see if something is true. So let's prove that the product from I equals 2 to n of 1 minus 1 over I is actually equal to 1 over n for all n greater than or equal to 2. All right, so in our proof, now that we've got the statement in, let's just take a look at what we need to do. Let's look at the principle. It says, hey, we've got to prove that the statement is true at the lowest level value. Well, n naught is 2. So we're just going to first say let P of n be given as above because we don't want to rewrite it. And now we're going to work on our basis step. And we're told, hey, n naught is 2. So we're going to let n naught equal 2. And what do we wish to show? We wish to show that P of 2 is true. Now, this is P of n. Okay, so this is what we are given, that is P of n. Well, P of 2 just says everywhere you see an n, you're going to put a 2 and check it out. Okay, this is an I. All right, so this equation has a left-hand side and it has a right-hand side. And we're trying to prove that the left-hand side equals the right-hand side. Because we're going to try to prove that P at n naught is true. Okay? We're going to try to do the first step, the basis step. All right, so we look at the left-hand side of P of 2. Now, does this look familiar to you?
Yeah.
So what is the left-hand side of P of 2? And then we're going to look at the right-hand side of P of 2, and we're just going to check and make sure that those two sides really are equal to each other. So this is the left-hand side of P of n. This whole thing is P of n. So everywhere you see an n, you're just going to put a 2. So the left-hand side of P of 2 is what? Can you read it to me?
The whole thing, like n
Well,
over.
okay, let me show you how let me explain how we read this sort of
Uh-huh.
expression. We read product first. This is a big product. So it is the product from, start at the bottom, I equals 2 to n of, and then whatever this expression is, 1 minus 1 over I. So it's the product from I equal 2 to n of 1 minus 1 over I. Now you try it.
Okay, so the product of I equals 2 to n
Uh-huh.
of 1 minus 1/2.
Okay. Well, let's put, instead of the n, since it's going to be P of 2, let's put the 2 there
Okay.
for n.
Okay.
It's not a half, it's not a 1 over 2
Oh,
yet.
because I, my bad. I'm sorry.
Yeah, right. But
Right, right.
because we're still sitting
Yeah.
inside that product. But you're right. I is only going to have that single value of 2. So it is 1 minus a half. And of course, what is 1 minus a half?
1/2.
All right, now let's check the right-hand side. There's not a lot of work to do here at all. It's deceptively easy, right? The right-hand side of P of 2 is just, well, it's 1 over 2 because we just replaced the n with a 2. So P of 2 is true since the left-hand side equaled the right-hand side. Okay? So that's the basis step. You always want to show that it's true for that bottom level value. And a lot of times it's deceptively simple. Now, we need to show that P of K implies P of K plus 1. That means that we assume P of K, it's going to be a direct proof, and we wish to show P of K plus 1, because this is an if-then. If P of K, then P of K plus 1. All right? So in our inductive step, just to remind us what we're doing, we're just going to prove that P of K implies P of K plus 1, okay? Just to help ourselves. So we're going to be talking about K. Reader has no idea what K is. So let's tell the reader, let K be some integer. And since we want to be able to get off even the bottom level step, like we're assuming that whatever step K we're standing on, we're just assuming we're standing on step K, and then we're going to try to prove we can step up. Well, we want to be able to get off that bottom step. And that means whatever argument we give just now in this inductive step, it better work to help us get off the bottom step. So we go ahead and say, hey, K could be equal to that bottom level N naught, but N naught was actually 2, so I'll put that there. But in general, whatever N naught is, you want K to start there, okay? We assume P of K. And then a minute here, we wish to show P of K plus 1, okay? But let's just, let's go ahead and write down P of K, because we really need to know what it is we have in our hand. So can you read what this would be if instead of an N, there would be a K where the N is?
Yes. Okay. So the product from I equals 2 to K of 1 minus I,
1 over I.
1 over I equals 1 over K.
Nicely done. Very nice. So that is our inductive hypothesis. This is our money in the bank right here. We're going to spin this. To get to, to buy our wish. Now, help me with the wish, because I want to get a real good look at what we really wish to do. Can you please help me with what P of K plus 1 would look like? Can you read it to me as if it,
The product from I equals 2 to K plus 1 of 1 over 1 minus 1 over I equals 1 over K plus 1.
beautiful. That's perfect. So now we can slide up, because we see everything we need to see. I'm going to just put a little cloudy, dreamy wish around that so I don't accidentally think that I can start with that. It's just a dream at this point. But we want to show this is true, this equation. We have this to use. We'll be, using substitution with that. Does that all sound familiar?
A little bit, yes.
All right, well, let me show you the big tricks that we had learned. One of the things we practiced was breaking off the last term of a sum or a product. Okay, we had some quizzes on that, and we practiced it in class as I do now. All right, so what we're going to do, this is our strategy. Since it's an equation, a formula involving a big product, we're going to start with the left-hand side of P of K plus 1, and we're going to work on it using legal algebra, things we may assume without proof, using our inductive hypothesis, some more algebra, and we're going to turn it into the right-hand side. That's our strategy. Start with the left-hand side and show it's actually equal to the right-hand side. So it's always the strategy with these formula induction proofs, starting with the left-hand side of P of K plus 1. We can't start with P of K plus 1. We may not start with this whole equation because we don't know that it's true. but we're certainly allowed to look at the left-hand side of it and see what other ways it could be equally written. So we start with the product from I equals 2 to k plus 1 of the quantity 1 minus 1 over I. All right. Now, we want to get this to look like that. It's a long cry. However, we could just use this induction hypothesis here, then it might be able to make at least part of this product look more like what we're shooting for than this looks like. At least it's a fraction that we would get, right? It's not the right fraction, but so since we want to be able to use this product from I equals 2 to k, and we have a product from I equal 2 to k plus 1, we can break this into two products. Does it really matter how we group the factors when we're multiplying a bunch of stuff together? It does not. Let me just show you what's really going on. This is 1 minus 1 over 1 times 1 minus, oh, sorry, start at 2. 1 minus 1 over 2 times 1 minus 1 over 3 times dot, 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 times 1 minus 1 over k times 1 minus 1 over k plus 1. Do you agree that this expanded view is really what this product represents?
Yes.
And see, what we're going to do is we're going to say, oh, it's just a bunch of stuff getting multiplied together. It's just fine if we group these together and multiply them all together first. And then at the end, we'll multiply by this piece. That's what we're going to do. We're going to take the product from I equals 2 to k of 1 minus 1 over I. That's all of these. So I'll put that in red. That's these. Times this piece, which is the product from I equals k plus 1 to k plus 1 of 1 minus 1 over I. It's just that single term where I takes on the value k plus 1. Do you see that this is really the same thing as that?
Yeah.
You don't sound convinced.
No, I see it.
Okay. Well, that's why we learned that skill of breaking off the last factor, or if it's a sum, you break off the last summand, and this is a plus instead of a times. But the reason we do it is, hey, inside the red here, I should have done it in green, but whatever, we're going to spend this money because the product from I equal 2 to k of this expression is equal to 1 over k, according to our inductive hypothesis. So now we're getting ready to use our inductive hypothesis. This is equal to 1 over k times this last broken off term, which of course is just going to turn out to be this in the next step. But I just want to do these in two different steps because this is the inductive step. This is by induction. When we say by induction, we're saying, oh, we're spending our inductive hypothesis money and making the substitution from here to here. And then we just use a little algebra. That product I only takes on that single value, k minus 1. So this is 1 minus 1 over, excuse me, did I say k minus 1? I meant to say k plus 1. See how this just turns into that? Now, are you with me?
Mm-hmm.
Well, just keep your eye on the prize. We want this. We started with this. See, we started with that left-hand side. We're trying to turn it into 1 over k plus 1. Well, we're better off than we were when we were here, but this still does not look like 1 over k plus 1. Okay, but we can make it look like 1 over k plus 1. There's a couple of ways to do the algebra. Okay, so I'll show you two different ways to do the algebra here. One way is to distribute this 1 over k across this binomial. So it's 1 over k times 1, which is just 1 over k, minus 1 over k times k plus 1.
Oh, Professor, I don't think I can see like the paper.
Sorry.
All right, thank you.
I'm just taking this 1 over k, and I'm multiplying it across this binomial. So it's 1 over k times 1, that's just 1 over k, minus 1 over k times 1 over k plus 1. That's 1 over k times k plus 1, because I'm just multiplying. 1 times 1 is 1, and k times k plus 1 is just k times k plus 1. That's one way to go. I prefer to do this. I'll just keep that 1 over k sitting there for the moment, and here I'll get a common denominator of k plus 1, because I want to add two numbers where one of them has a denominator that's non-trivial. So to get the 1 over k plus 1, I have to multiply it by k plus 1, right? And then this minus 1 is already over k plus 1, so I can just put that there. I like this one better because k plus 1 minus 1 just becomes k. And then since we're multiplying, the k up here cancels with the k down there, and we get the 1 over k plus 1. So I like this way better. But you could do it this way, and then we're still, no matter how you slice this piece of cake, you got to deal with a common denominator, okay? Because here we're subtracting two fractions. Here we were subtracting two fractions. You don't maybe think of one as being a fraction, but it is. It's a quotient. It's 1 over 1. But anyway, here we've got to get a common denominator. Oh, well, what's the common denominator here if we're going to subtract these two?
Okay.
You got to have enough to build the denominator of both of these. So it's going to be k times k plus 1. We want the bigger one, okay? Like if it was 1/2 and then 1/10, the common denominator, you take the bigger one. You take the 10th,
Okay.
right? So it's kind of the same idea here. All right, so the 1 is over k, but we want to put it over k times k plus 1, so it still has to get multiplied times k plus 1. And of course, this 1 is already over the k times k plus 1, so it's still just a minus 1 there. And we're back to the same idea. This becomes k over k times k plus 1, and then the k's cancel, and we're left with 1 over k plus 1. But any way you slice it, you can get the right-hand side of p of k plus 1. Remember, if we go back and look at our wish, that's what we were trying to get. So either way you go, we get the right-hand side of p of k plus 1. So what did we just do? We showed that, hey, if we're standing on step k, then in fact, we really can step up and stand on step k plus 1. We just proved p of k plus 1. So p of k does imply p of k plus 1, because we started only with this assumption that p of k is true. We wish to show this, and we did do by starting with the left-hand side and turning it into the right side. And finally, we invoke the PMI, right? By the PMI, we can now say that product 2 to n of 1 minus 1 over I is equal to 1 over n is true for all n greater than or equal to 1. 2, excuse me. So we did work this in class, this particular problem. And I think we might have worked another one, or maybe this was a WebAssign problem. We might have worked the one in class where it's the product from I equals 2 to n of 1 minus 1 over I squared. And I think this turns out to be n over n plus 1, if I remember correctly. So why don't you try that one? And then you can look at the class notes from section 5.2 and see if you are able to do it.
Okay.
Let's see if this is right. 1 minus 1/4 is 3/4, but this is 2/3. Oh, it's not right. I wonder if this is supposed to be n plus 1 over n plus 2. I think it's supposed to be n plus 1 over n plus 2. Let's see. That certainly works at the bottom because when n is 2, this becomes 3/4. And this is 1 minus 1/4, which is 3/4. I think it's right. Maybe you better check the notes first just to see if it is right. We can quickly
Okay.
check it though. 1 minus 1 over I squared, the product from I equals 2 to k, times 1 minus 1 over k plus 1 squared. And this is going to equal k plus 1 over k plus 2 times k plus 1 squared minus 1. Don't do it this way. I'm just trying to check it to make sure it's right. Oh, yeah, it is right. Because then we've got, yeah, k plus 1. And this is k plus 1 squared minus 1 over k plus 1 squared. Oh, we're multiplying, yeah, so the k plus 1. So we've got k plus, oh yeah, what is this? K plus 1 quantity squared minus 1 over k plus 2 times k plus 1. And what is this? This is k squared plus 2k over k plus 1 times k. Yeah, this works out. Now I should get k plus 1 over k plus 2. I'm not sure this is right. I'm not sure this is true. I think I'm misremembering this. Hang on. Let's go to the book. See, like I said, it's hard to just come up with these. Let me share my book with you and let's take a look. Are you still there?
Yeah.
All right, let's go to WebAssign. So you've got some WebAssign up. Are you Monday, Wednesday, Sean?
No, I'm Tuesday, Thursday.
That's right. You're Tuesday, Thursday. Okay, so there's WebAssign that's due on the end of the week. Let's go to the ebook. Go to chapter 5-2. Okay, there we go. All right, this is the one that I was just, this is the right one. This is 1 minus 1 over I, the product from I equals 2. Okay, so, but then there's another one. Where is it? There's a bunch of them. Great problems in here. Oh, this is the one that's n over n plus 1. It's a sum of 1 over n times n plus 1 from I equals 1 to n is equal to n over n plus 1. But hang on. This is the one I was talking. Oh, no wonder I was so far off. Look at it, it's number 16. It's a 1 minus 1 over 2 squared times 1 minus 1. Look, it's not anything close to, well, what I was saying. It's n plus 1 over 2n. No wonder. Oh, no wonder. All right. No wonder I wasn't able to get it. But you can check, look how the answers are here for some of these, Like, you can go and just like, pull down the answer thing if you're confused. Like, go ahead and write down some, go ahead and check these out. Use the answer key on the ones that are in the back of the book. Anyway, you can look at a lot of them. This is the one. It's number 16 in the ebook. exercises. I'm glad I checked because you would be very frustrated trying to prove something that wasn't true, right? I'm glad I checked it because it wasn't working out. Okay, other questions? We're running toward the end of our time, but Sean has had a lot of questions answered. So if anybody has other questions that they want to have answered, some burning question that has arisen during the course of our office hour, please do ask. Shakira, did you have a question that you wanted? This is no good.
No, not necessarily. You pretty much covered what I was really stuck on, which was the extra credit. But besides that, I don't have any other questions.
Okay. Well, I am still grading test 3 for Tuesday, Thursday, folks, but I have got it graded for Monday, Wednesday, folks. So I need to get back to my grading, unless you've got a question, Stephen, that you've thought of.
No, I'm good.
All right, folks. Well, y'all have a good night, and I'll see you this week.
All right.
Thank you.
Thank you, Professor.
You're welcome. Thanks for playing.